So this is question 4 of the Cert Higher Level Applied Maths, and it kind of involves just differential equations as a whole. So a ball of mass m is projected at initial velocity 15 meters per second vertically downwards into a tank of water. The ball travels through the water against an upward buoyancy force that is 4 times the magnitude, the weight of the ball, and a drag force mv squared newtons. So the first thing we're told is to draw a diagram to show the forces acting on the ball when it's moving downwards. So we can imagine just the ball is sort of in a tank of water. So it's just the surface of the water. And when it's in here, if you read the question, it will have its weight downwards, mg, and it will have an upwards buoyancy force and a drag force. Now the buoyancy force is 4 times the weight of the ball, so it's going to be 4 mg, and a drag force mv squared. And it's accelerating, well, it's mostly accelerating upwards, but that's going to be the direction of motion that's going to be traveling. Show that while the ball is moving downwards, the rate of change of its velocity v with respect to distance s is v dvds is minus 29.4 minus v squared. Okay, so this v dvds we can actually do fairly easily. So a is the rate of change of velocity over time, which we can split up as dv ds times ds dt. Now ds dt is just v, which is v dv ds. So that's the acceleration. So now we can use Newton's second law, which is F equals m v dv ds. Now the net force as it's going down will be its weight minus the drag, or minus the buoyancy force minus the drag force, is mv dv ds. Now every term has m common to it. Now minus 3 by 9.8 is 29. It was minus 29.4. So it's minus 29.4 minus v squared equals v dv ds, which by symmetry, I'll just write it in the question, the way the question wants me. QED. And to solve the differential equation to find an expression for v in terms of s. So, one thing we can do is we can divide both sides by the entire quantity of minus 29.4 minus v squared and multiply across by ds. And then after, we can integrate both sides. So I'll just do that. So we're going to integrate. Now, what are the bounds of integration? Well, initially, it's at a depth of 0. You're going to have the displacement as 0, and it has initial velocity 15, and we're looking for v and s. So, in solving this, I'm actually going to factor out a minus. So, if we just turn that into a plus, and just bring a minus out here, just to make it easier to integrate. Now, if you remember partial fractions in a case, you can use the fact that if you differentiate the bottom, we get 2v. Now, if we do v over what it's differentiated as, we get 1/2. So the 1/2 is actually the scaling factor that we need. So that'd be 1/2 natural log of the bottom, so 29.4, that's v squared. And that's just the integral of this. So this is minus, bounded between 15 and v, of 1/2 log of, I'll write it as v squared plus 29.4, is s between 0 and s. So I'll just write it the other way around. So s is minus, I'm going to start from here, so 1/2 log of v squared plus 29.4 minus 1/2 log of, now it'd be 15 squared plus 29.4, which is 254.4. 254.4. So what we actually have is 1/2 log of 254.4 minus 1/2 log v squared plus 29.4. Now we can factor a half out, and we get log 254.4 minus log v squared plus 29.4. Now, using the log law, that log a minus log b is log a over b. This is now s equals 1/2 log of 254.4 over v squared plus 29.4. Now it's saying for v in terms of s, and we have s in terms of v. So it's going to be slightly harder to manipulate, but we have to do it representing v in terms of s. So the one thing we can do... Now, this would actually be helpful for part 4, but we have to write it v equals blah blah blah. So if we multiply by 2 and e both sides, we get e to the 2s is 254.4 over v squared plus 29.4. Dividing by e to the 2s and multiplying by this, we get v squared plus 29.4 is 254.4. And I'll write it e to the minus 2s. So v is just, alright, 254.4 e to the minus 2s minus 29.4 under the square root in meters per second. And that's v in terms of s. That should be 29.4. Okay, the ball is at maximum depth d when v is 0. So v is 0, s is capital D. So d is 1/2 log 254.4 over 29.4 because v is 0. So I'll just calculate this 1/2 log 254.4 over 29.4. Now it doesn't tell us to what degree of accuracy. So d is 1.078956579 ... So I'll write d is 1.08 meters to 2 decimal places. After reaching its maximum depth, the ball changes direction. Draw a diagram to show the forces on the ball. Okay. So again, we're in this tank of water, and now the ball is traveling upwards. So I'm not sure... if you've done physics, you will always know that the buoyancy force acts upwards. It does say upward buoyancy force, but it could trip people up if they never met the term before. But we're going to have the upward buoyancy force acting here, which is 4 mg. And then we're going to have the weight of the ball acting downwards, as well as the drag force of mv squared, because drag naturally opposes motion. So as the ball is kind of resurfacing, the drag will be against this direction of resurfacing. Now, write in a differential equation to write the change of velocity v while it moves up through the water. So now we're taking upwards as the direction of motion. So 4mg minus mv squared is mv dv ds. Because it doesn't say velocity v over time or by distance, so I'll just write it as dv ds just for symmetry. So that'd be 29.4 minus v squared is v dv ds, and it didn't tell us to solve it, just told us to write it, and that's what it is. So that's the end of question 4, leaving us with applied maths.